Good morning, children. So far, we have seen AC chapter, how AC behaves with the inductor, capacitor, resistor, etc. We have seen the power dissipation. We have seen that the resistance offered by an inductor is known as inductive reactance, represented as XL, and it is equal to L omega. We have seen all these. So now what we are going to do is we are going to make combinations like LR circuit. That is a circuit in which an AC circuit in which resistor and inductor are connected in series. Let an AC source V0 sin omega t is connected here and I current flows through the circuit. Here is a resistor, so there is a voltage drop across that is VR. If I is the current passing through the resistor and R is the resistance, this VR will be equal to I into R. Similarly, the voltage across the inductor is VL, which is I into XL, that is I into L omega. Now let us analyze how the current and voltage are related in all these parts. In resistor, we know that current and voltage are in phase. That means if V equal to V0 sin omega t, I is I0 sin omega t. They are in phase, there is no phase difference. But in the case of an inductor, if V is V0 sin omega t, the current and voltage are not in the same order. They are not in same phase. Current lags by pi by 2. That is, if V is V0 sin omega t for inductor, I is I0 sin omega t minus pi by 2. So this, if we show in a phasor diagram, if we can show it in a diagram, that is actually our phasor diagram. We first show the resistor, voltage across the resistor, that is VR, and the current, they are in phase, same phase. So they should be on same line, VR and I. Now, in the case of inductor, the current lags, which means voltage is leading by 90 degree, pi by 2. So from here, 90 degree voltage across inductor should be marked, VL. So the current should lag behind VL by 90 degree. Now let us check what is the resultant of these two velocity. Let us make it as a V. We will mark it as V. And let this V resultant voltage makes an angle phi with the current. We take everywhere current as standard. From current makes an angle phi with the resultant voltage. So consider this triangle alone, which is plotted here. VR here, this is VR, this line VR, and this triangle, this length will be equal to VL. This length and this length will be equal, so this is VL. So from this triangle we can apply Pythagoras theorem. V square is equal to VR square plus VL square, or V is root of that VR square plus VL square. Now substituting this VR is IR and VL is IXL. Substituting these two values, we get V equal to root of IR the whole square plus IXL the whole square. Here we have I square, here also I square. That I we take outside. So here I is here, I is outside the root of remaining R square plus XL the whole square. Now this I, if I bring here, it will become V by I, which is the effective voltage by the current, which we get it as root of R square plus XL the square. So this effective voltage by the current is nothing but the effective resistance offered by inductor and a resistor together, which we call with the name impedance. So impedance is the effective resistance or effective reactance offered by inductor and a resistor together. When AC flows together, inductor and resistor, what resistance they offer, that is called impedance. Now we have the previous figure in that VR was here, VL is here, and V is here. So VR is the voltage across a resistor, VL is the voltage across inductor, and V is the resultant voltage. So the same diagram we can draw in terms of resistors also, that is a reactance also. Here resistance value, here inductive reactance, and here the impedance, total resistance. So from this triangle we can write a tan phi as opposite side, that is VL by adjacent side, VL by VR, or XL by R. XL is L omega, so L omega by R. So phi is the phase difference between current and voltage in the circuit, that is in effect the phase difference between current and voltage. So in this case we can see that voltage leads current by an angle phi, and that phi is calculated as tan inverse of XL by R. Now let us consider a CR circuit. That means in the previous case we saw LR circuit, here we have CR. So as usual, here we have a capacitor connected and a resistor, they are in series. So the voltage across capacitor is VC and the voltage across resistor is VR. We know VR and current, voltage across resistor and current are in phase, but in the case of capacitor, voltage lags by current, or current leads by pi by 2. That is, if V is V0 sin omega t, I is I0 sin omega t plus pi by 2. That is, current is a little advanced than the voltage across capacitor. So the phasor diagram we can draw. First we will mark the resistor, across resistor voltage VR. VR is the voltage across resistor. Current is in the same direction, same phase in the case of resistor. So single line for VR and I. Now voltage across capacitor lags by pi by 2. So from here pi by 2 back, 90 degree back with VR, or with the current 90 degree back VC. So here is a VC, from here 90 degree back VC. Now they will make a resultant, that is V marked here, and there may be an angle phi from the current to the resultant voltage, that is phi. So once again, as in the previous case, we apply Pythagoras theorem, substitute I values. V by I, in this case we get R square plus XC the whole square, XC square, root of R square plus XC square, where X is the capacitive reactance, that is 1 by C omega. So XC was 1 by C omega. Now ZRC is the impedance of RC circuit, that is the total effective reactance offered by capacitor and resistor together to the flow of AC. Now as in the previous case, we can consider the impedance triangle. This impedance triangle will have a resultant here V or Z. We can draw both, that we can draw here. If you see resultant voltage across capacitor, voltage across resistor, angle phi, that we can draw in terms of resistance also, that is a resistance R, capacitive reactance XC, and impedance Z. Same way from here we get tan phi is equal to VC by VR or XC by R. X is 1 by C omega, then 1 by C omega R. We get the phase difference phi, and here we will understand voltage lags current by phi. Now let us consider the LC case, the inductor and capacitor connected together. So more than this usual way of LC connection, here there is a special case of LC which is called a LC oscillator. For example, if we connect a charged capacitor with an inductor, there occurs electrical oscillations, that is energy from capacitor flows to inductor and the energy from inductor flows to capacitor. So there is a oscillation of particular constant frequency, and that particular circuit is called LC oscillator. So this is an LC oscillator. We have an inductor here and a capacitor here. Capacitor is charged and there is a switch. You close the switch, charge flows from capacitor and current flows through the inductor. So when current flows through inductor, what happens is it creates a magnetic field around it. So because of that, there is a voltage drop, an EMF induced. That induced EMF is calculated as L di by dt. If I is the current, L di by dt. So there is a voltage across capacitor and there will be a voltage across inductor. Voltage across capacitor we can find using basic definition of capacitance, that is C is equal to Q by V. And voltage across inductor we calculated as L di by dt. Now this circuit behaves like, as I said, first when capacitor is charged, when connected to inductor, current flows through inductor. Inductor creates magnetic energy. So once maximum current flows through capacitor, maximum energy reaches inductor. So capacitor loses its charge. Energy of capacitor loss. Once the energy of capacitor is lost, almost zero, the energy in inductor will be maximum. After that, again back to capacitor, charge flows from inductor. So once again capacitor gets charged, that time current in inductor is almost zero. Likewise, there is an energy oscillation. This exchange of energy is called a oscillation. So electrical energy is stored in capacitor and the magnetic energy in inductor. So let's apply some mathematics here. We consider this a circuit. So let's consider Kirchhoff voltage rule here. This is a loop. So the sum of voltages is 0 as per Kirchhoff rule. So VC, voltage across capacitor, VL, voltage across inductor. If you add up, it should be 0. So voltage across capacitor, as I said, which is Q by C, and VL is L di by dt. We'll divide this equation throughout with L. Then it becomes Q by LC plus di by dt equal to 0. That term di by dt is written here and Q by LC is written here equal to 0. Then we know from the basic definition of current is charged by time. So we can write as dq by dt. I alone we will write as dq by dt. So d by dt of dq by dt plus q by LC is 0. So it will become d square q by dt square plus q by LC equal to 0. So this equation has a speciality. This is similar to the equation of simple harmonic oscillator. And as per simple harmonic oscillator, in 11th standard you have seen the equation d square x by dt square plus omega square x equal to 0. So this is also similar, d square q by dt square plus q by LC equal to 0. So they are comparable. If so, here this 1 by LC is nothing but omega square. So let's see those equations again. This was the equation d square x by dt square plus omega square equal to 0. Omega square x equal to 0. So here instead of x we have q, and instead of omega square we have 1 by LC. So omega square is 1 by LC. Omega is 1 by root of LC. Also omega is 2 pi frequency, 2 pi into nu. Therefore nu is 1 by 2 pi root LC. So this is the equation for the frequency of oscillation of an LC circuit, an LC oscillator. The frequency of oscillation of energy in LC oscillator. So we have already told the energy is in inductor, it is magnetic energy. So we write as EB, energy due to magnetic field B. And in capacitor, energy is due to the electric charge. So EE we write, E suffix E. Electrical energy, magnetic energy. So total energy is sum of electrical energy and magnetic energy. We have studied about energy stored in capacitor, that is half epsilon 0 E square. Half epsilon 0 E square. The energy, similarly the energy in inductor will be, instead of E square you can replace it with B square. Half is here. Instead of epsilon 0, 1 by mu 0 you substitute. So this is the equation of energy stored in inductor, magnetic energy in inductor. So after this oscillations, after a long time, when the energy oscillates between capacitor and inductor, finally the energy, the oscillations die out, because there will be heat loss. The energy will be lost as heat and also as electromagnetic radiation. So these LC circuits are used in tuning circuits, like in our radio, wherever you have tuner circuits, all we are using this kind of LC combination.